In this video, I'm going to describe how to do optimization of one variable functions. Optimization is a procedure that's used to find locations of what are called local max and local min. Local maxima are locations on a graph that look like the top of a hill. So on the graph that's shown here, there'd be all the locations that are marked with an orange dot. Local minima are locations on a graph that look like the bottom of a valley. So on this graph, they're all indicated with green dots. If we examine this graph in terms of its derivatives, what we'll notice is that each of these locations where there's a local max and a local min, the tangent line of the function has a slope of 0. Now the slope of a tangent line comes from the derivative of the function evaluated at that point. So that means that at each of these locations, if we were to take the derivative and evaluate it at the corresponding x-coordinate, we would get an output of 0. So f prime of x is equal to 0 at each of these spots. This gives us a powerful strategy for determining where some of the local max and local min of a function can occur. Now it doesn't capture all of them, because sometimes the local max and local min can have this shape or that shape, so a sharp point. At those types of locations, there is no tangent line. If you zoom in close enough to those points, they'll never flatten out to a curve with any particular slope. They'll stay as sharp points forever, no matter how far you zoom in. Whereas for the smooth curves, like the curve in blue at the top, if you zoom in close enough to a smooth curve, it'll eventually look like a straight line. It'll eventually look like its tangent line at that point that you're zooming into. So anyways, we're missing these two types of shapes of max and min. Those come from the first derivative not existing, and we'll ignore those inside this course. We'll ignore that possibility. The other thing we have to be careful about is just because the derivative is equal to 0 does not mean, it's not very good, does not mean that the function has a max or a min at that location. For example, here, the tangent line goes horizontal, but there's no max and no min. So when we set the derivative equal to 0 and solve for x, we're going to need a method to diagnose, first of all, whether it's a max or whether it's a min, because both of them have that same behavior, both of them have a derivative of 0, or whether it's neither. So to remind you how that process works, here's a nice function. It's a polynomial, a quadratic, and we're going to go through the process for finding the max and min. Our first step would be to take its derivative and set it equal to 0. Then we would solve for x. This process would give us what are called the critical numbers. The critical numbers of the function are candidate locations for local max and local min. If we wanted to be extremely careful, we would also look for locations where the first derivative does not exist, because those can also be locations of max and min, as long as they're in the domain of the function. Anyway, so for this function, if we do that process, take the derivative, set equal to 0, we get one critical number, x equals -1. The second step that we would do is we would have to diagnose whether the critical number is a max or a min. And then we have two methods. The first method is the first derivative test, also called the increasing-decreasing test, and it works as follows. We would draw a number line, or our number line would span the domain of the function. We would cut the number line at our critical number. We would choose a test value to the left of the critical number, and it could be anything like -3 or -10 or -1 million. And we choose a test value to the right of -1, let's say 5. And what we would do is we would plug those test values into the derivative. And it's kind of like -3 tells you what the behavior of the derivative of the function entirely. The whole thing to the left of -1 tells you what its general behavior is. F prime of -3 is, let's see, f prime of x is 10x plus 10, so -30 plus 10, we get -20, which is negative. And that means the function decreasing on this side. Remember that derivative tells you the rate of change of the function. The fact that the derivative is only equal to 0 at -1 means that, it's not like it could possibly be switching its behavior at -10 from negative to positive, because Switching from negative to positive means it has to switch and eventually hit 0. And we only found there's one spot that the derivative is equal to 0, it's equal to -1, so that means it can't switch its behavior. Whatever it's doing at -3, it's doing on that entire side. So it's decreasing on that entire side. To the right of -1, we pick 5. We plug that into the derivative, so f prime at 5. We plug that in, we get 50 plus 10, we get 60, which is positive. So that means to the right it's increasing. And if you look at the arrows, something that's going down and then back up, that's the graphical feature of a minimum. So local min at x equals -1. And then we would get the y value by evaluating f of x at -1. The second method we could use to diagnose a critical point is called the combo test, or the second derivative test. It works by taking the critical number that we found and plugging it directly into f double prime of x. F double prime is the derivative of the derivative. If we plug -1 into the second derivative and something positive comes out, then that means the function's concave up in that region. Concave up is like a bowl facing up, and a bowl facing up is the shape of a graph around a minimum. If instead we plug in the number and get something negative, so something that has that concave down shape is what a negative second derivative means, then it means that critical number is a local maximum. For this particular function, f double prime of x is a constant. The derivative of 10x plus 10 is just 10. 10 plus 0, which is 10. And that means the function is concave up everywhere. We have a critical number. The function is always concave up, so that critical number must be a min. Both the first derivative and the second derivative test work well for this function. Some functions the second derivative test will not work for. What will happen is you'll plug the critical number into the second derivative, and instead of getting something positive or something negative, you'll get a 0 coming out, and that tells you nothing. It gives you no information. You have to go back to the original function, or you have to go back to the derivative and do the number line analysis, do the increasing decreasing test. Just to go over that again a little bit in some more detail about why does the increasing decreasing test work. If this graph on the left-hand side indicated a bank account as a function of time, there's regions where the bank account's going down, regions where the bank account's going up. Regions where it's going down, those are regions with a negative rate of change. Rates of change are obtained from the derivative. So, wherever the function's decreasing, so wherever the bank account's going down, those regions would be indicated by a negative derivative. Regions where the bank account's going up with time would be indicated by a positive derivative. If we have a region, or we have an x-coordinate, where to the left of that x-coordinate, the function's increasing, and to the right of the x-coordinate, the function's decreasing, so it's going up and then back down, that's the shape of a max. So that would be like this region up there. There's a maximum around there. It's going up and then back down. But if there's a minimum, the shape of a minimum is always the function's decreasing, switching to the function increasing. So like this region over there. So that's why the increasing decreasing test can be used to diagnose critical points. We check the behavior of the derivative to the left of a critical point, the behavior of the derivative to the right of the critical point, and then compare the sign, whether it's positive or negative. The concavity test, or second derivative test, or combo test, works because these tangent lines behave in a particular way for concave up and concave down regions. So I'm going to draw a few tangent lines here. So this might be a slope of -5. This might be a slope that's a little bit closer to horizontal. So instead of a slope of -5, it'd be a slope of -2. Bottom one is a slope of 0, and then we have a slope of +2, a slope of positive 5, and notice that the derivative, or the slopes of these tangent lines, is increasing as we go from the left to the right. The slope of a tangent line comes from the derivative, so this means f prime of x is increasing. If f prime of x is increasing, that means that f prime of x has a positive derivative, and the derivative of f prime is f double prime. So the takeaway is whenever a function has this shape like a bowl facing up, its second derivative is going to be positive in that region. And the graph that's below, it's the opposite. The tangent lines are decreasing. So I'll just do 3 here. M is equal to 5, m is equal to 0. Now we have a negative slope, m is equal to minus 5. F prime of x is decreasing. So the derivative has a negative rate of change, which means the second derivative is negative. So bowl facing down means negative second derivative. The combo test is essentially extracting this shape information. We get the critical point, we plug it into f double prime. If f double prime is positive, it means the function has the shape like the graph on top, which means that the critical points can be a minimum. If f double prime is negative, it means the graph in that region has a shape like the bottom graph here, which means the critical point corresponds to a local maximum. Go back to this picture and we see that it matches perfectly. That maximum, every maximum that you see, concave down. So f double prime is negative. For the minima, the function is concave up, so f double prime positive. I'm going to go through one example. I'm only going to use the second derivative test here. We could use the first derivative test, it'll work just fine, but I want to practice the second derivative test. So f prime of x. Oh, I should indicate what we're doing in these steps. To find the max and min, our first step is to find the critical numbers. So f prime of x, take the derivative, we get 12x to the power of 2. No, it's 12x to the power of 3, sorry. Plus 12x to the power of 2 minus 24x. Then we want to find where the tangent line is horizontal, so we set the first derivative equal to 0 and solve for x. On the right hand side, it's wise to factor. I'm going to common factor out of 12. I'm going to common factor out an x, and we're left with 12 is out, so I have an x squared left plus an x minus a 2. Next, I'm going to factor that quadratic using the product and sum method. I want two numbers that multiply together to give me negative 2 and add together to give me positive 1. So the answers will be plus 2 and minus 1. Multiply to give me negative 2, add to give positive 1. And then I want to look for all possible x values that will make left-hand side equal right-hand side. So how do I get 0 on the right? Well, I can get 0 on the right if 12 times x is equal to 0. And that means that x equals 0 is a solution. I can get the right-hand side equaling 0 if that second bracketed term is 0. Because I'll have whatever the first piece is times 0 times whatever the third piece is. So it'll be something times 0 times something, which is 0. That's going to happen if x is negative 2. Or the last piece might be 0, the last bracket, so x is positive 1. Those are our critical numbers. Now we're going to do step 2. We're going to diagnose the critical points. There's no number line needed, there's no test value needed. It's relatively clean. We just find f double prime of x. It's best to go to the pre-factored form. So the polynomial, like the 12x cubed form, so 36x squared plus 24x minus 24. We can factor. It might make our task slightly easier. I'm going to factor a 12 out, and that's all we can take. And then we're left with 3x squared plus 2x minus 2. And then I'm going to evaluate this second derivative at each of these critical numbers. So f double prime at 0, we get 12 times 0 plus 0 minus 2. So we get negative 24, which is negative. So f of x is concave down. So this shape at x equals 0, that means it's a max. And we could plug that into the original function and get the corresponding y value. F double prime of x at now negative 2. So we're going to have 12 times 3 times 4 minus 8 minus 2. We get positive 24, so something positive. So f of x is concave up, has this shape at x equals negative 2. So min at x equals negative 2. And then the last critical number, I can plug in positive 1. So we have 12 times 3 plus 2 minus 2. That's 12 times 3, which is 36, which is positive. And that means f of x is concave up there. At x equals 1, so there's a min at x equals 1. So that's the combo test, second derivative test. And in this example, it worked out cleanly, worked out neatly. So I already mentioned all of this, that the second derivative test can fail. If it fails, it'll fail by giving you a 0 when you plug in the critical number, which gives you no information. It doesn't give you any concavity information. In that case, you'd go back to the first derivative test and check if it's increasing and decreasing on either side of that critical number. And again, also that it doesn't catch all of them. This process, we didn't check for where the first derivative doesn't exist. Now, for a polynomial, that's not going to give us solutions, but for other types of functions, it might. Just something to be aware of in general. I'm going to go through two word problems now that build on these optimization skills. The first one is a standard problem that you should have done in your previous calculus course. It's a fence problem. It may have been the first one that you did, or maybe the second one that you did, because this is the one with the twist. Farmer has some fence, 160 meters of it, and wishes to build a rectangular fence along a river. This means that no fencing is needed along that side where the river is located. What should the dimensions of the fence be in order to maximize the area enclosed? So here's your river. And I'm going to draw the fence. It has to be a rectangle. And there's different ways that we could draw that fence. We could say, well, I'm pretty sure it's going to be a square shape, because isn't a square the most efficient use of fence? Like, isn't that whatever, what we were told? The closer to a circle it is, the more efficient the use of the perimeter, like some vague argument from whatever grade that was. So shouldn't it be that? Or maybe someone says, actually, well, the river is kind of like free resources. It's like free fence. So why don't I use all of the river that I can? Like, I'm just gonna look at all that free fence I can use. If I make it really skinny like this, then I've made better use of the free resource that's given to me. The free, effectively a free side of fencing. And the truth of the matter, the real answer is kind of going to be intermediate. The most efficient use of amount of fencing in terms of extracting or creating an area for a given perimeter is indeed a rectangle, but is a square, all sides equal. But we have that free side, we have that free resource. So our answer is going to be close to a square, but not exactly a square. Let's see how to get that nice answer. So I'll draw it like this. It'll look something like that. But even if we drew it wrong, even if we thought it was a square and just drew it that way, or we thought it was like this and drew it that way, wouldn't matter. The calculus will work. Now I'm going to label these sides. I'm going to give these sides names. I'm going to say this amount of fencing is called X. And then since it's a rectangle, the other side is the same. I'll also call it X. And because the other side is going up and down, hey, I'll call it Y. So I made a picture and I labeled it. Our goal is to maximize the area. So we need a mathematical expression that represents the area so we can maximize it. So we can take its derivative, set it equal to 0, and solve for x. The area of a rectangle, fortunately, is an easy formula to remember. The area of a rectangle is length times width. So it's x times y. All right, so we take the derivative, set it equal to 0, solve for x. Problem is that we have two variables here. This is a two-variable function. It's a function of x and y. We need to reduce it, at least if we want to use the methods that we learned, we want to reduce this to be a function of one variable. What we have not done yet is we haven't made use of our information inside the question. We are told that there's 160 meters of fencing. This is called a constraint. (160 meters of fencing). If we didn't have a constraint, we'd just say build an infinitely big fence because you'll get infinite area. So the constraint is absolutely necessary to make this a meaningful question. How do we build it in though? Well, 160 meters of fencing, we have to make an assumption that it's best to use all of it. So like don't use 150 and just have 10 off to the side and be like, yeah, I don't need that. I can maximize without it. You're going to use all of it. Now, you're going to use it by building the fence along all those three sides. If you add up the sides of those three sides of the fence, it should add up to 160. So I'll put that in mathematical terms, that the first side plus the second side plus the third side must equal 160. And I'm going to collect like terms, 2x plus y is equal to 160. And that gives us a relationship between x and y. I'm going to rearrange it. I'm going to get y by itself, 160 minus 2x. And now what we can do is we can substitute that in for y inside of our area expression and make it a function of one variable. And now we're done the hard part. So a is equal to x times y, which is equal to x times 160 minus 2x. So a is equal to 160x minus 2x squared. This is now a calculus problem. This is like one of the ones that we started with. So now we'll do calculus. Let's take the derivative, set it equal to 0. A prime is equal to 160 minus 4x. So 0 is equal to 160 minus 4x. Add 4x to both sides. Divide both sides by 4. So we get 40. It is not nice at this point to declare victory. I'm going to circle it, but we're going to do a check. We have to make sure it's a max. So I'll put max, question mark. Let's take the second derivative. The derivative of 160 is 0. The derivative of negative 4x is negative 4. So the second derivative is always negative. always, well, so a double prime evaluated at 40 is equal to negative. It's always negative, including at 40. That means it's concave down, which is a max. Because once in a while, you'll try to maximize something and you'll find the minimum, which may mean that there is no max, or it may mean something else. You missed it. You only found the min. That check is important. It is not something to skip ever. You always want to make sure that the critical point does what you're after. Okay, the next fence question isn't much different, except you probably, well, some people do one like this and some people don't, whereas this one is fairly standard. So this farmer has 160 meters of fencing as well, wishes to build a rectangular fence, but doesn't have a river. Instead, this farmer wants the fence to be not fully enclosed, wants it only 1/3 enclosed on one of the sides. This problem comes with a diagram, and it comes with a very convenient labeling that avoids fractions. So instead of calling that top side x and the bottom part 1/3 x, the top side is called 3x and the bottom side is called x. We have to be careful interpreting our answer, that's all. So the question is the same. What should the configuration be? Should this one be a square? Should I have more going up and down or more going left and right? Like what should the geometry of this fence be in order to maximize the area enclosed? So we're going to set it up the same way. Our area, our goal, I should be consistent. Our goal is to maximize area. Area enclosed. The area is equal to the length times the width. And in this case, our length is 3x and our width is y. Now we have to look for the constraint. Our constraint is, if we add up all the sides, it should use all 160 meters of fencing. So the first side, 3x, plus the second side, y, plus the third side, x, plus the last side, y, is equal to 160. It's a perimeter constraint. The perimeter must total amount of fencing that's used. We can collect like terms, so 4x plus 2y is equal to 160. I'm going to rearrange. I'm going to get y all by itself. So 2y is equal to 160 minus 4x, and we can divide both sides by 2, 80 minus 2x. Okay, now let's do the substitution thing. A is equal to 3xy, which is equal to 3x times 80 minus 2x, which we can clean up. A is equal to 240x minus 6x squared. Now we can do calculus. We have a function that we're trying to maximize. Okay, so a prime rather, we get 240 minus 12x. We're going to take the derivative and set it equal to 0. We're going to add 12x to both sides, and then divide both sides by 12, and we get 20. Max or min. So let's find a double prime. A double prime is equal to the derivative of a prime. Derivative of 240 is 0. Derivative of negative 12x is negative 12. So always negative, always concave down. A double prime at 20 is negative. So it's a max. Has this shape. So that's our answer. And actually, I should go back to the previous question. If x is 40, what's y? Y is equal to 160 minus 2x. So 160 minus 80, so 80. So for this first question, it should be an 80 by 40 fence. And for the second question, let's find y as well. Y is equal to 80 minus 2x. So 80 minus 40, which is 40. So the fence is 60 by 40. 60 because the top is 3x, 40 with the part going up and down, the y value is equal to 40. Fence is 40 by 80. Should be consistent x by the y value. Another thing you can do with these is you can experiment. You can say, okay, 60 times 40, 2,400 square meters. Can I do better than that? Can I mess with it a little bit, like change the x to 19 and figure out what y has to be? Y has to be 80 minus 2 times 19, and then multiply those two numbers together and see what happens. See if your answer is larger or smaller than 2,400. And if this is really the maximum, then you should be able to beat that value as long as you don't violate that constraint. As long as you don't violate the constraint that y is equal to 80 minus 2x. That's one flavor of optimization. So problems that are predicated on geometry, or questions where you're given the mathematical model, where you're given the function. Another type of optimization is one where you have to build the function. You have to do a little bit more. This one example of this is business optimization. There's a few key formulas and key ideas that are needed to do business optimization. One of them is the formula for total cost. So for costs, for a process or a company or whatever it is going to be a combination of variable costs, which depend on how much of something you do or how much of something you make, and fixed costs, which are independent of how many things that you make, for example. So if you have a donut shop, your variable costs are like materials, ingredients, things that you need to buy more of if you sell more donuts. And then there's fixed costs, like what's the lease per month that you pay to have the facility. That it doesn't matter if you sell 0 or you sell 1 million, you're paying that same lease. So that'd be a fixed cost. And it's important that you can distinguish between them. Another quantity or formula that we are sometimes interested in with business optimization is the average cost. The average cost is defined as the total cost divided by the number of units that are made, or the number of units that are done. So it's, if the total cost is C of x, then the average cost is C of x divided by x, if x stands for the number of things that you're making. And then another formula is the total profit. Profit is defined as how much money you bring in minus how much money goes out. Your revenues minus your costs. You might have several revenues and several costs. So your total number of revenues minus your total number of costs, that's your total profit. We would put all of our revenues together and call them capital R of x, put all of our costs together and call them capital C of x. Sometimes you have to build the functions a little bit carefully. You might be given a unit cost, for example. So to make one donut, let's say the unit materials cost might be 10 cents. If you wanted a function that would give you the cost of making X donuts, it would just be the unit cost multiplied by X. To make 10 donuts, it would be the cost per donut times 10. To make 100, it would be the cost per donut times 100. To make X of them, it would be the cost times X. For revenue is the same. If you're given a unit revenue, like how much money do you bring in for each unit sold? So let's say you make You bring in $1 for each one that you sell. How much would you make if you sold 20? Well, it would be 20 times 1. How much would you make if you sold X of them? It'd be 20. It'd be 1 times X, or whatever X is equal to. Now, just as a comment, sometimes costs and sometimes revenues are linear, like here, and sometimes they're nonlinear. Give you an example of an optimization question that's kind of given, that's all put together nicely, or pretty nicely. So Waldo, famous Waldo, has a side business making snake diapers. Snake diapers must be a very, very small market. So a very small market size. And Waldo estimates that revenues for these snake diapers would be given by, if he sells X of them, would be given by X multiplied by 80 minus X. So that would be dollars per week if he makes X boxes, actually. Not X diapers, but X boxes of snake diapers. Waldo has fixed costs of $1,000 per week to run this special diaper line on top of his other signature products. Who knows what those horrifying things are. Waldo's variable cost is $10 per box of diapers. How many boxes of snake diapers should Waldo make per week to maximize profit? If this was a real problem, the answer would be 0. There is no market for snake diapers. But this is a math problem. It's not constructed to be real. It's constructed to give nice numbers. So let's work through it. P of X, our profit function, is equal to a revenue function, R of X, minus our cost function, C of X. Our revenue function is given to us on a silver platter. It's given to us for free. We don't have to think about it. We don't have to do any work. It's X times 80 minus X. But our cost function is going to require some work. What is C of X? So our cost function is going to be equal to our fixed plus variable. Fixed costs plus variable costs. Our fixed cost is $1,000. Our variable cost depends on how many boxes we make. It says Waldo's variable cost is $10 per box. So we want to know how many to make. We don't know what that number is, so it's 10 times X, where X represents how many we're going to make. So I'm going to put that in for C of X, 1,000 plus 10X. I'm going to simplify. P of X is equal to multiply through 80X minus X squared minus 1,000 minus 10X. Carry the negative sign to the bracket. Now I'm going to combine like terms. We have 80X minus 10X. That'll be 70X. Okay, and now we have a mathematical model that's pretty easy to work with. This mathematical model results what the profit will be if we make X boxes of snake diapers. So let's find P evaluated, or P prime. We're going to take the derivative because we want to maximize it. We're going to do calculus. We're going to max it with calculus. So P prime of X, derivative of 70X is 70, derivative of X squared is 2X, and derivative of 1,000 is 0. This will always happen, by the way. Your fixed costs, if we're talking about maximizing profit, fixed costs disappear. They're not a factor. Nothing you can do about them. Average cost is different, but for maximizing profit, it's not necessary to keep it in analysis. Okay, next step is I'm going to set the derivative equal to 0. Right, I'm going to add 2x to both sides, divide both sides by 2. I'm going to declare victory, but I'm going to check if it's a max. P double prime is equal to 0 minus 2, so negative 2, which is negative. So it's concave down for all x. It's a constant, the second derivative. P double prime at 35 is equal to negative 2. So local min. oh sorry, local max. Concave down has this shape. Now the question only asks for how many boxes of diapers for snakes should we make. So the answer is just 35. If the question also asks what is the profit, we would take this number and plug it into our profit function, 70x minus x squared minus 1,000. And hopefully we would end up with a positive profit. Okay, and then one more example. This one's on average cost. So this Waldo fellow, in addition to making snake diapers, also makes bunny hats and estimates the total cost of producing X hats is given by 25,000. So that would be the fixed cost portion, plus 6x plus 10x squared. So there's a non-linear component to the cost. Maybe a certain amount of materials can be purchased for cheap, but if he wants to buy more, he has to go to a different supplier. That supplier charges an arm and a leg, charges a lot more, and that would be the nonlinear component. Or maybe the nonlinear component is the overtime to run the facility for a third shift. And to get anyone to come in for the third shift, you have to pay more. And that could be built into the model in a very approximate way like this. Anyway, not important. The model's been given to us. We can't complain about it. We're just going to work with it. How many hats should be made to minimize the average cost per hat? So total cost is given. The average cost has to be constructed. So from the formula sheet, average cost, C bar, is equal to our total cost, C of x, divided by x. I'm going to take each of those terms and divide it by x. So I'll have 25,000 divided by x, plus 6x divided by x, plus 10x squared divided by x, which we can simplify. 25,000 x to the power of -1. I'm doing that because we're going to have to take a derivative, and this will save us from having to do a quotient rule, plus 6 plus 10x, using exponent laws to cancel the powers. Now we can do calculus. Now minimize it. Calculus. So I'm going to take the derivative of C bar, and take the derivative of the average cost. Well, the first part, we have the power rule, the -1 will come down. We'll have -25,000, x to the power of -2. Derivative of 6 is 0, and the derivative of 10x is 10. We're going to set the derivative equal to 0 since we're looking for a critical number. So 0 is equal to -25,000. I'll put this back as a x to the positive 2 in the denominator, plus 10. I'm going to add -25,000 over x squared to both sides. 25,000 over x squared is equal to 10. I'm going to cross multiply by x squared. 25,000 is equal to 10x squared. Then divide both sides by 10. 2,500 is equal to x squared. And then what is x going to be? So we take the square root of both sides. And we technically get two solutions. We get x is equal to 50. And we get x is equal to -50. But this is how many hats should we make? Negative hats is not a good idea. I'm going to say x equals 50 is the answer, but we're going to do a double check. We're going to make sure that this is a minimum. Check if x equals 50 is a min, not a max. So C bar double prime, we take the derivative of the derivative, we're going to get positive 50,000 x to the power of -3 plus 0 plus 0. I'm going to plug in 50, C bar double prime at 50, which is 50,000 divided by 50 to the power of 3. And I don't really feel like calculating that. All that I care about is that this is either a positive number or a negative number, because I want to know if it's concave up or concave down. This is a positive something divided by a positive something, so it's going to be positive. This means it's concave up, which is this shape, which is a min. So we found the number of hats to minimize the average cost per hat. We should make 50 bunny hats.